Okay, so thanks everyone for joining. Today we have Qian with us, and he will talk about fast and parallelizable logical computation with homological product codes. And Kian is currently a postdoctoral fellow at CalTech, working with John Preskill. And in the past, he was a graduate student working at Chicago with Liang. Liang is young, right? I mean, you were
Yeah.
student of Liang, right? Okay. Okay, very nice. So yeah, like several people are interested in basically this product codes nowadays, and yeah, like let's say, but he has somehow, the logical computation, he has made it fast and parallelizable, which was a big, I would say, bottleneck with some of these quantum LDPC codes. So maybe Kian, you could, yeah, like please start.
Yes, thank you so much, Kisha, for the very nice introduction. So I guess I don't need to introduce myself anymore. Yeah, I'm glad to be here to talk about our recent work titled Fast and Parallelizable Logical Computation with the so-called homological protocols, which I'll introduce later. So this is a joint work with Hengyun Zhou from Harvard, Guo Zheng from Chicago, Dolev like Pablo, and also from Harvard, and Misha from Harvard, and my former advisor Liang Jiang from Chicago. So before the talk, I want to mention that like I'm not sure about the background of this audience, so I try to keep the talk at keep the slides at a high level. But feel free to interrupt me and ask in-depth questions at any time. So, so the motivation for this work is that we want to get photon quantum computation, FTQC, with low space and time overhead. Namely, we want to implement some quantum computing tasks like reliably without using too many physical qubits, or using a circuit that's too long. So to make sure everyone is on the same page, let's so review this overhead problem that exists in quantum mechanics in general. So the idea of performing some photon quantum computation is that we take any task that performs some useful computation, and then we replace the circuit with, in general, a wider and a deeper circuit, so that now we have some redundancy in the system that we can use to identify and correct the errors of the qubits and the gates, so that we can simulate the original circuits reliably, even in the presence of false. So, for example, one canonical way of doing this is to replace each of the bare qubits here with a D by D patch of the so-called surface code. And then now, as you can see, the total number of physical qubits will be k times d squared. And this actual d squared factor is what we call the space overhead, because you now need like a d squared more physical qubits in order to do the same task with like photons. And in addition, we also have we also need to perform some photon operation on this encoded error correcting codes. And then, for instance, the standard way of doing this logical operation for the surface code is like using a lattice surgery. So the idea is really you can think these different logic qubits, different patches, as different tiles of different things, and then now you can move these different tiles around, and then merge and split them, very much like playing a game. And then people show that in order to make this kind of lattice surgery operation for photons, so you have to do usually D rounds of some syndrome extraction circuits in between different logical gates. So that means that now the circuit is also like a D times deeper than the original circuits. And this factor D is what we refer to as time overhead, because that means that the circuit is a bit longer. Okay, so obviously one major problem of the surface code scheme, of this photon scheme using the surface code, is that the space overhead grows too quickly with the distance of the code, with the size of your lattice. And in practice, in order to perform very reliable computation, we really need a distance about 30. So this translates to we really need roughly 1,000 physical qubits just to get one logic qubits. And in a case where you need like thousands of logic qubits to do some useful algorithms, this easily gives you requires like millions of qubits. So this is clearly beyond the range of current or even near-term devices that we can imagine. Okay, so to sum up, those leading fault-tolerant schemes using the surface code suffers from a very large space overhead, and that means that we do not expect we can scale to a large quantum computer using this kind of codes. Okay, so one possible solution to this space overhead is to use this recently advanced so-called quantum low-density priority check codes, QLDPC code for short. So the idea is that, as you can see here, the problem we have this like large overhead is really because we are only having encode one logic qubits in using a large patch of physical qubits. So it's, in other words, this encoding is very sparse. It's very sparse encoding. And recently people show that if you can relax the connection between your qubits, say if you allow some interaction between this distance pair of qubits, then you can actually use a much better codes that can now encode say many logic qubits in the same block. So here, so each of the logical qubits, you can think that is represented by one of these blue bars. So you can really have like many logic qubits encoded in the same block of physical qubits. So in that sense, you have a very high encoding rate, and then consequently you have a very low space overhead. And in the extreme case, people show that you can even find the codes where the number of encoded logic qubits scale linearly with the system size, and therefore you get a constant encoding rate and therefore constant space overhead. So in other words, now if you do this encoding, then the number of physical qubits required for this entire quantum computer is only a constant factor larger than the original number of these bare qubits. Okay, so so that's nice. But the question is that we also want to have some kind of low time overhead, right? So and then so it turns out like there's no free lunch. So by using this code, while even though you can get much higher encoding rate, but somehow because these logic qubits are now somehow overlapped together, it becomes like generically harder to address so individually these logic qubits and to perform these logical gates. So the leading approach, so before our work, was but still using this kind of lattice surgery idea. So for example, and the idea is still to perform some lattice surgery operation for these QLDPC blocks by interfacing these blocks with some surface code ancilla, essentially. So as an example, in our early work, so we have this variant of this coherent scheme where, say, whenever we want to address one logic qubits, let's say a logic qubits that sit on the boundary of this memory QLDPC code, we kind of pair it with a surface code, and then we can teleport this information from this logic qubits to this surface code patches by doing this lattice surgery, and then we perform the logical gates there and then teleport it back. So you can really think that we still need to rely on some sort of surface code as some sort of like processing code to do the logical gates, and then the QLDPC code is essentially just used as a memory. Okay. And although you can perform universal computation with this kind of lattice surgery scheme, but what is the consequence? It turns out like because the surface code is still have very bad encoding rate, so you can really imagine that one surface code that has one logic qubits already have a size that's very comparable to this giant QLDPC memory block, and therefore in order to maintain this low constant space overhead, you can imagine that maybe you can only use one or two surface code ancilla at a time. That means that you can only perform, say, one or two logical gates on this memory block at a time. So that means that now you actually have all these operation logical gates now have to be like serialized. And this gives you actual effective K in the time overhead. And oftentimes we will consider the total space and time overhead, not multiplication of these two. You will find that you end up with very similar space-time overhead compared to the surface code. So in other words, in this picture, the idea of using the QLDPC codes is only a way of trading time for space, but now like you're not gaining much from in terms of total space-time overhead. So this is the major problem we want to tackle. So basically, how can we say design?
Sorry, Qian, can I ask one question? Yes,
Sure.
on this slide, what is D in this case? Because in the previous one, D is the size of your surface code, that right?
Yes. So here D is the distance of the code. So for any
Okay.
quantum, you can define a distance, right? So we always use a D to refer to the distance of the code.
All right, thanks.
Okay, so therefore the task of this work is to design more efficient logical operations that's better than the lattice search for those carried QLDPC code, so that you can not only have this low space overhead, but also a low time overhead for computation. So so what is the high level idea we'll use?
So it was KD square, right? Let's say if you go, and here it's K square D, right? Like in the surface case code, like what was the circuit size of, like the space time overhead overall? Like I mean, if you go in the previous case, like the surface code case, it's KD square, right? Oh, it's KD cube.
It's KD cube, yes. And then
KD
here
cube
is K squared D. But the idea is that but if you consider, say, some couple graph protocol as example, then K equals D squared. So like K squared D is the same as KD cube, for example.
K equal, like, which code you mentioned? Like
for couple graph protocols, for example, where
I mean, so for SGP codes. Okay. Okay. I see.
But if you use codes with even better distances, the things get even worse. You end up with even worse space-time overhead by using the QLDPC codes because of the K factor.
So let's say if I think about the good QLDPC codes, right? Where let's say K scales like D. So in that case, we have like D cube here, and in the other case we will have like D to the power 4. I mean,
so in this case it's even worse. So if you use a good code, it's even worse. So that means that for those code with very good distances, like serializing this operation is going to give you even worse overhead. Okay, does it make sense?
Yeah. Mm-hmm.
Okay. So what is the high level idea we want to use to design this more better logical case? So as you can see, the problem with this lattice search is really like even if you can do some selective, say, targeted logic operation, and you get universal computation, but it's not parallel. You cannot like do many operations at a time. But in contrast, one can think about another type of logical gates one naturally have for almost any stabilizer course that has more like the opposite feature. So the idea is to consider this like a transversal logical gates, so between any two CSS quantum codes. We know like for any two CSS quantum codes that each encode some many logical qubits. So each of the orange, like the green 3D balls, represents a logic qubits. And then the idea is that given they take two copies of the CSS block code, and then you apply the physical transversal gates. Okay, so let me really clarify what I mean by the transversal gates. So the idea is really you to overlap these two code patches, and you apply this pairwise signups for those qubits that have the aligned coordinates. So there's a global operation. And then turns out this transversal physical gates will give you exactly the transversal logical gates between basically this pairwise logical signups between this block of two blocks of logic qubits. So apparently this operation is highly parallel. So you can do this for all the entire code logic qubits at the same time. But unfortunately, so you lose the selectivity. That means that this operation, you have to apply the same operation on all the logic qubits because they are sort of overlapped together on the same physical block. So you cannot like say only address the subset of logic qubits. And therefore, this operation alone is not very useful because you cannot even get a universal set of gates. Right? So if you compare these two schemes, one is selective, the other is not parallel, but the other one is parallel but not selective. So therefore, the question we ask is that can we actually get something that aligns in between those schemes and get simultaneously selectivity and parallelism.
But like let's say if you're interested in like there are those kind of circuits, like let's say quantum Fourier transform, where you want to implement hard mod on all of the gates, then you could use like this second approach, right? I mean, just like
exactly. So using
yeah.
these global gates, you can implement certain maybe very structured tasks. But for sure, we'll also get to this point later. So we'll actually explore this factor to do efficient logic operation. But I guess for universal computation, you still need some operations that can do this local and like a selective operation.
Yeah.
Okay. So the question is therefore, can we get something in between? So the idea we use is it turns out we can actually improve or use some variance of this, have some variance of this transversal signals. Okay. So as you can see here, if you talk about this transversal signals from another perspective, let's say you can use a left patch as some data block, and you can use the second patch as the ancilla block. And then if you can now perform some stain measurements, which is say you prepare this ancilla in some 0, and you apply the transversal signals, and you measure this ancilla, then that gives you some poly measurements on this data block. Okay. So and then the reason you do not get a selective operation is really because you're actually using exactly the same ancilla codes, and they encode many logic qubits. So therefore, but the question is that can we actually design a smaller ancilla code, use a smaller ancilla code that encodes only a subset of the original data logic qubits? And then let's suppose we can still implement this transversal signals, which means that we can still perform this pairwise signals between those aligned logic qubits. Then now we can use this ancilla to address only this subset of logic qubits. In this case, just the top right 4 logic qubits. And then apparently, this kind of scheme is both parallel and selective in the sense that you can still perform many measurements on the data block by using like say a still LDPC ancilla that encode many logic qubits. But in addition, if you can like sort of selective ancilla in some arbitrary fashion, then you can address a arbitrary subset of logic qubits, and therefore you get both selectivity and parallelism. So let me pause a second, and this is really the key idea of this entire talk. Let me know if you have any questions.
So by doing this selection on your ancilla qubit, do you get to implement more transversal gates compared if you just you don't do the selection? Is that kind of
exactly? So if you don't do this, say, transformation on ancilla, you only get a transversal signal that will act globally. But now, if you can say transform ancilla, you can sort of shape your ancilla in a certain way. Then it's still essentially a transversal signal, but you can do these signals in a more flexible way, essentially. That gives you, say, local operations and a universal set of gates.
Right. But if you don't do the lattice surgery, then you probably still won't get a universal transversal gate set, right? But you just get more compared if you just don't select the ancillary set.
No, we can get a transversal Clifford group, although we still have to do magic distillation. Okay. But at least for the Clifford operations, we can only use these transversal operations. That we'll show later. So we'll completely get rid of the lattice surgery. So that's the key part of this work.
All right. Sounds good. Thanks.
Okay. Okay, cool. So how do we do this? Do this essentially like, how do we like generate a small ancilla and do this transversal signals? So apparently this will depend on codes, because we do not have a universal scheme of doing this operation. And then the codes that were used to demonstrate this kind of useful logical gadgets is the so-called like homological product codes. So let's start from the simplest example, which is the so-called hypergraph product codes, which is essentially by taking the product of like two repetition code. So here, let me try to introduce the notation and repetition that were used for this codes. So here, so I'm showing a code that's a product of 2 classical codes. Each of the classical codes represents by essentially a bipartite tanagraph where so the circles represents the classical bits, and the squares represents the classical checks. And there should be some edges connecting this base and the checks that are associated with this check matrix. So I'm not showing these connections for simplicity. And then now we construct the quantum objects, our quantum bits, the qubits, and the quantum checks by essentially taking the Cartesian product of these classical objects. For instance, we can construct the qubits by taking the product of a circle and a circle, and a vertical square and a horizontal square. Okay, we get 2 blocks of qubits. And then similarly, we construct a quantum X check by taking the product of a vertical circle and a horizontal square. And we do the similar Cartesian product for the Z checks. And then we assign the connection between these quantum objects to be the same as this of this horizontal codes. For instance, we assign the vertical connection between for all these different columns to be the same as this vertical code, and we assign the horizontal connection for these different rows to be the same as this horizontal code. Again, I'm not showing these connections for simplicity. And one nice thing about this hypergraph protocols is that you can define a so-called canonical basis for these logical operators. So the idea is that whenever people talk about logical qubits in a block code, what they really mean that they really refer to some basis of logical operators, logical Z and X logical operators that represents logical qubits. Okay, so the structure of this, so there's very nice structure of this logical operators for this quantum code, which is they are essentially just the duplicates of these classical code words into different rows or columns. For instance, we can find one code words of this horizontal code indicated by this blue bits, and then we duplicate them on the first row. Then we get the logical Z operator on the first logic qubits. And similarly, we can find a code word of this vertical code, and we duplicate on the first column. Then we get the X logical of the first logic qubits. And we can similarly find some other code words and we duplicate them into different columns or rows to get some other the logical operators of other logic qubits. Okay. And in addition, we show that so there's additional structure for this logic operator. So which is you can really so now we can label in this logic. So we're representing the logic qubits again using this 3D balls. So we can effectively think that okay, there are like I say 9 logic qubits that are encoded in this block sitting on the side. And then now we can choose this basis such that these logical qubits are, you can think that they are kind of associated with this top left physical block where the logical operators intersect. For instance, the first logic qubits with a coordinate 1, 1 is associated with so the logic operator with this very first logic qubits is only supported on the first row and the first column, and then intersect on this 1, 1 feeder qubits. And similarly, if you look at this pin qubits with a coordinate like 2, 3, then they actually have the logic operators that exactly only supported on the second row and the third column, and they intersect exactly on this 2, 3 feeder qubits. Okay. So in other words, you can really think that the logic qubits are somehow effectively sitting on the top left corner of your physical block. Okay. So why do we do this? So the idea is keep in mind that we want to perform some, so we want to essentially delete some of the logic qubits in this data block to construct a small ancilla block. And if we know the structure of these logical operators, it's much easier to delete some of the logical operators here. For example, one can construct an ancilla code by essentially deleting this first 2 bits of the horizontal code, which corresponds to deleting the entire first and second column of the quantum bits and checks. Okay, so this is deleting the bits for the classical codes is also referred to as a puncturing operation in the classical literature, if people are familiar with it. Okay, so why do we do this? So the idea is that we can easily say that now this ancilla code will only encode the last column of logic operators, because the first two physical columns are already moved, are already removed throughout this procedure. And we know that because we know that logical qubits are essentially sitting on the top left corner. Then we know that these logic qubits are also getting removed throughout this procedure. Okay. And it's very important that like the structure of the remaining logic qubits, let's say if you look at these pink qubits, they are still locally the same as the original codes. So in other words, this transformation, this removing procedure is some sort of structure preserving map that locally preserve the structure of the code. And it turns out because of this nice property, we can still implement a transversal synapse between these two patches. So the idea is that we still sort of overlap these two patches and you apply the physical synapse on this remaining set of qubits. And then that gives you a logical synapse between these logical qubits. Because in this case, more concretely, you will have the circuits that look like this. So you have a pairwise synapse between the 7 logic qubits and 7 prime, 8 and 8 prime, and 9 and 9 prime. Okay. And now we can take one step further and use this smaller ancilla codes to perform this kind of generalized steam measurements that only addresses a subset of logic qubits, and more specifically in this case, only the last column of the logic qubits in this data block. Okay. Therefore, we have.
Is it like is the idea you want to use? So is the idea that instead of using those surface codes, you want to use these punctured quantum codes to like to perform the like the transversal measurements?
Exactly.
Like transversal operations.
Exactly. So the reason you don't want to use the surface code is that it only includes one logic qubits. That only address one logic qubits in the data block. But now if you puncture this code, and then you can say that this puncture code is essentially another hypergraph protocols. And then it's possible, and then it still encode many logic qubits. Therefore, you can do many operations in parallel. That's the idea.
But assume that but let's think about the case where like you have on every logical qubit you want to perform a different operation. Now in that case, you will need several such. I mean, will you need like several such punctured codes?
That's a very good question. So one thing I want to say that if you could arbitrarily remove the logic qubits in your ancilla block, then you can address arbitrary set of data qubits in the data block. But unfortunately, as we'll show later, this is not feasible. So we cannot arbitrarily remove the logic qubits. We can only remove the logic qubits in a specific pattern. So that means that we can only perform some structured operation on this data block using this gadget alone. But the point is that we can combine maybe several such operations to perform a very unstructured or very generic logical operation, as we'll show later. Okay. So if people are interested in the mathematical structure of this construction, feel free to. This gate is actually referred to the homomorphic synapse because, as I mentioned before, this synapse relies on a homomorphism between these two column codes, which means that you need to find some structure preserving match between these two column codes in order to make sure that this physical operation gives you a valid logical operation. And you can see that here the homomorphism of this quantum codes is really by taking the homomorphism of the classical codes. So in this case, puncturing this classical code actually induces a classical code homomorphism, and therefore we can get a quantum code homomorphism by taking the principal product of this classical puncturing homomorphisms. Okay, I'm not going into the details about these mathematical formalisms, but feel free to refer to Shi Lin's original paper and also our paper for more details about this kind of gadgets. But one thing I want to emphasize about this gadget is that it's naturally fault tolerant, because so first we can make sure that by doing careful puncturing operation, you can make sure the distance of the ancilla is preserved. So the distance is at least as large as the distance of the data code. In addition, this scheme only involves the transversal signals, which is naturally fault tolerant because it doesn't propagate errors, as we all know. And in addition, if you look at the same circuits, if you can also fault tolerant prepare this computational basis states for the ancilla, then and we also have the fault tolerant measurements for like a transversal measurement for any code, then the entire scheme is a trivial fault tolerant. And we know that for any CSS code, we can prepare this code states, this zero states reliable by simply measuring the stabilizers. And therefore, in that sense, this entire protocol is trivially fault tolerant. And then, as I've emphasized before, is obviously both selective and parallel using these sketches. Okay. Good. So this is the essential fundamental gadgets we'll use for this course. But now, I guess it's related to the previous question. It seems like we only can perform some restricted set of operation using only these gadgets. So therefore, the question is, can we actually perform, say, universal computation or some computation tasks like very efficiently use these kind of gadgets? So I'm trying to demonstrate this again, use the Hubble protocols. As the first example, I will show that we will try to perform some polyproduct measurements, essentially on this data block. So the idea is that in this example, as you can see there, we can only measure single qubit polys. And we know that this operation is not very useful because this single qubit polys cannot even generate entanglement, right? So now we want to take one step further and show that we can measure not only single qubit polys, but also measure product of polys. Then things becomes already more interesting. And before that, let's try to resolve one problem, which is, let's say we claim that we can do selective operation, but if you look at this kind of scheme, then apparently it's not quite selective in the sense that, let's say here, we have to address the entire third column simultaneously. So we cannot even measure single, just one of the logic qubits. So we still have to measure something like globally. So can we do this? Can we actually resolve this problem? And let's say, can we only measure and can we get a fully selective gates? Let's say we only measure the very top left logic qubits with this gadget. So the idea, it turns out we can do this by introducing another element for these gadgets, as we'll show here. Okay, so how do we do this? So we, again, in the first step, we construct, because we only care about this very top left logic qubits, then apparently we don't care about the third and second column. Therefore, we can just puncture the third and second column out in this ancilla code by using this puncture operation. And then now, if you were naively apply the transversal signals between these patches, you will end up with a similar results as in the previous case, where you will end up with measuring the entire first column. Okay, you're not exactly just measuring the first logic qubits, but we have an observation that if you can somehow like reset the second and third logic qubits, just 1 second. Let's say if you can somehow reset the second and third logic qubits of your ancilla patch to the plus state, then these two logic qubits will not get entangled with the data block, and therefore they're not relevant in this procedure, and you will end up with only measuring the first logic qubits. So you can effectively think that by resetting these second, third logic qubits, you are effectively kind of masking them so that they're not playing a role in this process. So how do we do this masking procedure? It turns out we can actually introduce a third block, sort of the ancilla of the ancilla. And here we puncture out the first logic qubits in this ancilla code, and we only keep the third and second and third logic qubits. And then we perform this X measurements, this homomorphic CNOT and X measurements on the third and second qubits. This suffices to reset those two logic qubits of the ancilla code in the plus spaces. And therefore, gives us the desired masking operation that we need. So to sum up, it's really by combining this puncturing operation that removes some logic qubits, and then we and this masking operation where we reset some logic qubits into the complementary basis, then we can measure essentially any single qubit police or any some pattern of single qubit police in a fully selective fashion.
But
Okay.
Qian, like, I mean, like, okay, so yeah, so this is nice. Like, I mean, so basically this puncturing and masking together is giving you, in certain sense, full selectivity. Like you can now apply any transversal operation, like, I mean, in a fully selective manner. But still, I think the overhead, I mean, there is this unwanted operation that you end up doing. I mean, it has no effect, but you know, like there are these, you know, like, I mean, these operations which you are doing on the masked logical qubits. I don't know whether that can be counted as some overhead.
So I want to emphasize we have the same constant space overhead because we only use 2 extra ancilla patch. And the time overhead is also constant because we only use a constant extra certificates. So there's no extra overhead. Does that answer your question?
Yeah. Okay. So if it scales as a constant, you know, I mean, it's okay. The constant should be small, but it's okay. Yeah.
Yeah. So you do have a constant maybe of 3 because you need like 2 extra patches. But I guess asymptotically, this is still very favorable overhead. Still very highly efficient operation.
Very nice.
Okay. So now, as promised, we'll show that we can actually use this kind of puncturing and masking to measure also products of poly operators, not just single qubit polys. So how do we do this? Let's say in this example, we try to measure a 4-body poly products that act on the top left logic qubits. So the way to do it is again using this kind of 2-step protocol. So in the first step, we just puncture out the third column logic qubits because they are not relevant. In addition, we actually needed some extra operation, which is called the augment. So I'm not going into detail, but the idea is that you can, so instead of, in addition to puncture some base of the cluster codes, you can also add some extra checks. In this case, the actual single check that connects the first 2 bits. Okay. The idea of the reason that you're doing that is that you're now sort of fusing these different logical qubits together. So that, for instance, originally you have like 2 logical qubits that are sitting on the first 2 columns, but now having this actual check to connect them, you can effectively, you're essentially merging these 2-column logic qubits into one columns. Or in other words, you can think you still have the 2 logic qubits, but you're preparing them in some Bell states. You can think them either way. And then now once you have this Bell states, then if you now apply this transversal signals, then you will end up measuring like product of polys, the correlated polys, not correlations between these logic qubits, not just single qubit polys. And that's how you get this product measurements. And now this is not quite exactly what we want because we'll also it turns out we can have again use another patch that do some effective masking operation. And in this case, the operation is a little bit more non-trivial. So this actual patch, what it does on this ancilla patch is that it first mask out the third pair so that they are not relevant in this procedure. In addition, it performs some Bell measurements on these two pairs so that you can end up with essentially some 4-qubit JC state. Okay, so now you can use this 4-qubit JC state to perform this 4-body poly products on the data patch as desired. So again, it's like a 2-step protocol with a constant space and time overhead, still very efficient operation. Okay, so let's put things together now. So what we can do now with this fundamental operation at the logical level can be really summarized using this graph. So here, so again, I'm arranging this logic qubit. So each of the ball represents just a logic qubits. I'm arranging the logic qubits on a 2D grid, and then what we do is that we now can take any subset of rows, any subset of columns, okay, and then we take the intersection of them. That gives us a subgrid of the logic qubits of the original grid, okay. And then we can choose a set of hyper edges on these rows, represented by these squares, and also hyper edges on these columns, represented by these horizontal squares. And then now we take the Cartesian product of these hyper edges, these squares, we get this like 3D diamonds. For instance, the first diamond, which is a product of this horizontal square and this horizontal square, will be essentially a weight 6 polys that acting on this surrounding 6 qubits. And similarly, we can get say this diamond, for instance, as a weight 4 polys acting on this 4 surrounding qubits. Now we can essentially measure all these diamonds. Okay, all these let's say these 4 diamonds in this example, representing 4 poly products in parallel in using this two-step protocol. Okay, then that's exactly the logical operation that we can do using this kind of this kind of gadgets, and we refer to this as GPPMs, which is short for Great Poly Product Measurements, because as you can see that we can measure some pattern of poly products in parallel, but it has to be in some pattern, and the pattern is more like a grid pattern, so which is you have to measure things that are a product of something, so that you have you have to measure things on a subgrid essentially. Yeah, so this is kind of at the high level what we can do with this kind of homological gates and this two-step protocol. I'll pause for a second in case there's any questions.
Okay, if someone's question, please unmute yourself and ask. Yeah, it seems like no question. Okay.
Okay, good. So yeah, so and as I said, like this operation is highly efficient because you have a constant space overhead and you can do things just in one logical cycles. Okay, cool. So let's now get one step further. As promised, we'll try to apply this kind of gates, new logical gates and operations that we have to get, like, say, more general quantum computation with low space and time overhead. But I guess this was related also to the previous question. People already observed that in some sense, these gadgets alone, this GPPM alone, cannot generate the even the Clifford group. For instance, this operation can only perform some CSS type of measurements. So you can only measure either poly products of X or Z type, but you cannot even measure, let's say, Y type of polys. And therefore, obviously, you cannot get the universal, get the entire Clifford group. But the idea is that we actually have some other cheap operations that people already very familiar with. And these operations, for instance, include this transversal synapse that I just talked about that act on the that have pairs of synapse on all the logic qubits. In addition, we also have this so-called full transversal gate introduced by Nico Brookman, where you sort of more or less applying very similar like transversal like operations. For instance, this so-called CZS gates is doing this following operation. So you apply pairs with synapse. So you have some diagonal line, and you apply the pairs with physical synapse that are folded along the diagonal, and you apply the S gates on the diagonal. Then this physical operation gives you the exact logical operation, which is if your logic qubit is on a 2D grid, they'll end up with a similar pattern, the same kind of logical operation. And then similarly, you can do this Hahnemann swap, which is you apply the Hahnemann gates on the diagonal logic qubits, and you swap the logic qubits along the diagonal. Okay. And then these operations are qualitative transversal in the sense that each of the physical operations only touches at the most 2 qubits in the block. So they're still naturally photones. And they are cheap to implement. Always they have the constant space and time overhead. And the idea is really like the idea is that neither this GPM alone or this global transversal gates alone do not generate the Clifford group. But once you combine them, then you can generate the full Clifford group. And then in addition, if we do magic state distillation, they end up with a universal gate set. Okay. And in addition to this operation, we also constructed a new kind of global sort of transversal operation, which is we qubits on a 2D grid. Now you can translate these logic qubits under periodic boundary conditions by simply permuting a filter qubits. So this is referred to as some sort of automorphism gates because it's based on some automorphism of the code. This turns out to be also used for the tasks that we'll consider later. Okay, so yeah, I showed it in this example. So now once you have this, you use these gadgets in this box, then you'll end up with a universal set of gates. Then you can implement a universal set of algorithms. Okay, and potentially with low space and time overhead. So okay, so if there's no questions, I'll proceed. But the idea here is that what I'm trying to show. Okay, so so what is the remaining problem? So the remaining problem is that so I guess now we try to implement some algorithms. Now this problem is also more like becoming a compilation problem, which is you have some elementary set of gadgets that can be implemented efficiently, and now you can compile your algorithm basically into these elementary gadgets. So this is really a new way of thinking about things with this QRDPC block. And then you shouldn't really think about the compilation in terms of the Clifford plus T. You should really quantify your cost of algorithm by thinking about how efficiently can you implement the algorithm using these elementary gadgets. And one potential issue with this type of compilation is that, okay, so it might depend on the algorithms. Maybe for some algorithms, the compiled circuits could be still very long, because say if you think you have some very unstructured operation, and then you compile them, let's say using the GPUMs or signals, then you might have to do it with like many sequence of test kits. Then in that case, you still have some large time overhead. So that's something you want to avoid, and that's something I want to show that you can actually compile circuits very efficiently using this set of gadgets. Okay. So one example I want to show is that if you think about this problem, this compilation problem, one natural concern one might have is that if you think about some task that you wanted to say perform some intra-block operations, let's say here you have so many lottery qubits encoding the same block, and let's say if very unfortunately you have to apply some very messy intra-block operations, intra-block signals, and harmonize in a very unstructured way, then it looks like this pattern of gates is not very compatible with this kind of set of gadgets you have. Then the question is that, let's say if you want to implement a layer of these gates, so what is the circuit depth you have to compile, you would have to use these gadgets? Okay, so so obviously if you were to try to implement this task with a surface code, as I showed before, you would have to serialize this operation. You only have to do one operation at a time, and therefore you end up with a depth that scales linearly with k. Okay, suppose you have like a order k Clifford gates here. But now the question is that can we actually do better with this kind of gadgets? So that's essentially what we want to get to. And turns out we can have we can construct some compilation scheme such that we can realize this arbitrary layer of gates, intra-block gates, with a depth that scale as k to the power 3/4. So although this is not like very favorable, but it's already the case that really they can do things with a sublinear depth, which indicates that you can already do things in parallel and with a better overhead compared to the lattice surgery. Okay, and also once you as we showed before, once you can do this compilation with a sublinear time overhead, then you will end up with a lower total space-time overhead compared to using the surface code as well, just using the surface code for this computation. Okay, but the question is that obviously we're not satisfied with this factor of k to the power 3/4, which looks still quite slow. So can we do better with this? So the idea is that the philosophy is that you probably, so it depends on compilation, you probably for more structured tasks, you probably want to compile your circuits, your algorithm into a more structured layer of gates rather than this unstructured intra-block signal. so that they are more compatible with these elementary gadgets, and they can be implemented with the even shorter circuit depths. Let me illustrate this idea with this canonical example. Let's say we try to do a logical task that basically very simple logical circuits that essentially just do this pairwise signals between these logic qubits. And then if you don't do it carefully, then you would naively just encode all these logic qubits. You put all the logic qubits into a, say, Hubble-Graph protocols block, into a QRDPC block. And then now we'll encounter this problem that we now have to do many of these intra-block signals, which is still quite challenging with this operation. And you might potentially end up with this k to the power 3/4 steps. But so obviously this is not not a clever thing to do. Rather, when you could consider another kind of encoding. So instead of putting all the logic qubits into the same block, you now put these qubits into 2 blocks of codes. So let's say you put all these black qubits into the first block, and you put these red qubits into the second QRTC block. And then now you can see that this signals now just becomes a transversal logical signals between these 2 codes, which can be simply implemented use one gadget, which is the transversal signal gadgets. Okay, so now the depth is essentially just a depth, it's just one. It's a constant depth circuit. Okay, so this is good. So as you can see here, we're now using more operations, we're now using better logical gates to do the same task. It's really about the compilation. So we're really compiling this problem into a more structured layer of gates. In this case, just compile them into this like a transversal gates, so that they can more efficiently be implemented with our elementary gadgets here. Okay, so and another thing I want to emphasize is that so as you can see here, and also related to the previous question, still like it's more efficient to implement those interblock, say signals interblock operations compared to those intra-block operations. So we want to, when we do the compilation, we want to compile the problem such that we can maximally leverage those parallel interblock operations, and meanwhile minimize this like a selective and random intra-block operations. And then in some sense, these kind of elements, the first 3 parts, can be summarized like at a high level with the following sentence. You want to compile your algorithms or your computation in a pattern that many logic qubits are essentially doing the same thing. For example, in this case, you observe that because many of the logical qubits are doing the same signals, then it's very easy to be implemented using this QRDPC book. I think this was also like nicely pointed out by Kisha early on when we consider, say, some like a Fourier transform. Okay, so this is really the philosophy we can explore to make things better, to further reduce the time overhead. So I'll pause for a second in case there's any questions. Okay, good. So let me try to illustrate this philosophy with maybe like more examples. So first example I'll illustrate is to generate a logical GC state across an entire QRDPC block in a constant depth. Okay, so a constant number of logical cycles. So so here again we represent the logic qubits on the 2D grid with this green box. And then the protocol is a standard protocol where we prepare all the qubits in the plus states, and then we try to measure the two-body polys to establish those entanglements. Now we can see that we can divide all these two-body checks into basically like 4 colors. Okay, so and each color of these checks can now be efficiently implemented using 1 GPPM because we call that they are actually in a grid pattern. So we're measuring for each of the color, we essentially measure things on a subgrid, and therefore we can do it with just using 1 GPPM. So therefore, in total, we can just establish all this entanglement using like 2 steps of GPPMs. Therefore, it's obviously constant number logical cycle. So very similar to these problems. So again, much better than the k to the power 3 over 4 for this particular problem. And the second example shows to perform magic state distillation. So here I'm considering this 15-to-1 distillation circuits introduced in this paper, where you try to get one higher fidelity CCZ magic state by consuming 15 noisy T states. So here, the idea is that we prepare some initial states. So here again, each of the SIC line represents a block QLDP cycles. It's not just one logic qubit, it's really just a block of logic qubits. And then we need to perform this parallel polyproduct rotation on these different blocks. So this is the key challenging part in this distillation circuits. And we can implement this polyproduct rotation by supplementing a extra block of T states, and then you perform this transversal polyproduct measurements, and then we measure this magic states, this ancillary block in some basis. Okay, so if we neglect these final measurements, everything is actually only require transversal signals, because you actually performing, as you can see here, the same polyproduct operations for all the different logic qubits in this block. So it's really, you can do this with a transversal signal. So it's highly efficient. Unfortunately, this final measurements on this magic states now breaks this transversal structure, in the sense that you now have to measure this like magic states in either the X or Y basis, depending on the previous polyproduct measurements. So now you can really think that for this particular block of logic qubits, you would have to measure them in a random X or Y basis. So because every qubit now have to be measured in a different basis, then always is not a transversal operation. So it's not like many qubits or logic qubits are not doing the same thing. And this is exactly where we need to use this selective GPPM gadget that we designed to perform this local selective operations. Okay, so we can take one step further and reduce this. We call this reactive measurements, and we can change these reactive measurements into a reactive state preparation problem. So the idea is that you can supplement it with another ancilla block, and you perform transversal signals, and then you do the bell measurements. But the ancilla now need to prepare in either the X or Y basis, depending on the previous measurements. Okay, so again, this is not transversal operation. So how do we do this with that? How do we implement this with our GPPM gadgets? So let's for simplicity only assume that we only use the diagonal logic qubits. See, if we consider this 2D array of hypergraph protocols, then we only try to use this diagonal logic qubits for this task. We can just neglect the rest of the logic qubits. And then now to selectively initialize this diagonal logic qubits, we can do this in essentially 3 steps. In the first step, we prepare everything in the class, and then apply the so-called CZS gates. Recall that the CZS gates applies S gates homogeneously on all the diagonal logic qubits. Then this gates will convert all this plus into the I states. Okay. Then in the second step, we apply the GPPM gadget to perform some X measurements on any subset of the diagonal logic qubits. So this suffices to reset any set of qubits into the plus states. And in combination, this suffices for our state preparation problems. So obviously, in this example, we can do it in a constant depth. But as you can notice, we can only get a constant depth to operate on a square root of k logic qubits on the diagonal. In order to apply the schemes to the entire patch, we essentially need to apply this procedure for a square root of k times. So this finally gives us a depth that's roughly square root of k log k. There's some subtle log k factor, but roughly you can say that we are doing this thing for repeat this procedure for square root of k steps. So that gives us square root of k depths for implementing this distillation. But again, as well, emphasize this is still much better than linear, because the square root of k is still highly parallel. Okay, so any questions?
Sorry, can you explain again why is it square root k?
So the idea is that you can you can think that you are really generating this resource state, this special party of states. You can generate like square root k number of these states in one step. Then in order to generate the k states, then you need to repeat these things square root k times. So that's where the square root k comes from. Does it make sense? I guess in other words, in high level, you can think that, okay, so we want to basically initialize all these logic qubits, the entire patch of logic qubits, randomly in either x and y. The way we do it is that we do this deprivation for the diagonal with one step, and then we sort of permute this logic qubit to the other part, and then we do the same thing for the diagonal logic qubits, and we permute them to the other part. Really, you can really think that you use the diagonal qubits as some sort of factory to generate this resource state, and you can only do this for diagonal qubits. Therefore, you have to do like a square root k times in order to generate an entire patch of resource states. Does it make sense? Okay, so let's proceed with the final example. This is very similar to the magic C distillation, so I'm not going into the detail here. The idea is that once you have this block of CCZ that are distilled, then you can also like sort of teleport them into some data block to perform this parallel Toffler gates. Again, sort of transversal Toffler gates on all the logic qubits encoded. Again, we can do this with the square root k log k steps by using this GPVM gadgets. So I'm not getting into the detail here, but it's using very similar ideas compared to this distillation problems. Okay, so once we have the efficient magic distillation and injection, we can also put them together and implement this so-called quantum addition problem, which is you do the addition on this quantum base, and this is an important subroutine for many quantum algorithms. For instance, the Shaw algorithms. So the idea is really that for this addition, usually you have like a different base, and then we observe the structure that you actually have the structure that like many of these different bits are essentially doing the same thing, because they're just simply doing the similar addition. Let's see if you have like x1, x2, and then y1 and y2, and then what you do is that you do x1 plus y1, and you do the same thing as like the x2 plus y2, because they're essentially doing the same sort of things for different bits. And if you look at the circuits, that really means that you end up with these circuits that can be compiled into this highly parallel fashion. So as you can see here, for each of the circuit depths, you're essentially repeating the same sort of operation over different blocks of your qubits, of your logic qubits. And very crucially, you actually end up with some Toffler gates, for instance, here, that also act like that are just like parallel Toffler on different like qubits, and therefore you can actually encode this problem using our QDPC blocks and try to leverage this interblock parallel gates, including this like Toffler gates that were just demonstrated. So overall, you end up with sorry. Okay, so you end up with the same square root k log k depths, essentially because you can implement this Toffler with the square root k log k logical cycles. Finally, I want to mention that so far this logical gadgets, this kind of homomorphic CNOTs, this local CNOTs can be applied not only to Hubble-Guard protocols, but also to like those half-dimensional homological protocols. For instance, we can also do it for a code that is a product of like 3 classical codes instead of 2 classical codes. Now you can think that because you're producting like 3 codes, then the logic qubits are essentially can be arranged in a cube, and then now you can construct an ancilla by essentially selectively removing some of the shades of the logic qubits, and therefore you can address maybe any subshades, subcube of this entire cube. So it's still using a very similar idea. So why do we care about this higher dimensional codes? So one thing is that they can support the so-called like a single shot city preparation, a single shot error correction. The idea is that when you have to, okay, you don't have to understand this chain complex. The idea is really like when you have like this high dimensional structure, then you can see that you now for this x checks and z checks of the codes, you actually they are now redundant in the sense that you can have some meta checks that checks those checks. So these meta checks are basically some extra constraint that these checks need to satisfy even in the presence of measurement errors. So that means that if you have some measurement errors on the system, then you don't have to, sometimes you don't have to repeat your syndrome structure. You can just, by using these meta checks to diagnose those measurement errors. And therefore, this can significantly reduce the length of the logical cycles for those logical gates. So in many cases, you can end up with truly like a logical operations that not only have a constant space overhead, but are also constant depths. Okay. So yeah, to sum up, for this high dimensional codes, we can also get perform like polyproduct measurements on some subcube of the logic qubits. And in addition, this because we have single shot state preparation, now we can implement these operations with a constant depth circuits. So they're even faster essentially compared to those like 2D code operations. Okay, to conclude, in this work we have constructed several selective and parallel logical gadgets for the so-called homological protocols, and using these kind of new gadgets, we show that we can perform logic computation using now only QLE-based blocks. So we can just get rid of all the surface code. There's no surface code here. We only use these higher QLE-based blocks, and now we can achieve like low time overhead while maintaining a constant space overhead. So in the future, so one natural thing is try to generalize these homomorphic gadgets that we have here to maybe like better protocols, such as this leaflet protocols or this generalized vesicles that have been, for instance, actively considered in some recent IBM work. And then because these codes have better parameters, then that means that we might be able to do better in practical regimes if we were able to generalize some of these constructions to these better codes. And then in addition, as our techniques also apply to the 3D and 4D codes, it's natural to ask to consider if we can also construct this transversal NUC gates for these codes, because we know that we cannot get a transversal NUC gate for the 2D hyperbolic protocols, but it is actually possible to get such gates for 3D or 4D codes. So one example would be the 3D surface code, where you have the transversal CCC. So now if you can do this, and if you also combine with our like local Clifford gadgets, then you might be able to do many more things more efficiently. And then finally, I guess so far, I didn't emphasize like for this logical cycle here is actually still refers to like a D code cycles, which means that you still have to repeat D times of your syndrome instruction in order to be fault tolerant. So there's a question that even for the 2D codes, can we actually reduce this logical cycle to a constant by using so this recent idea it's called correlated decoding algorithm fault tolerance that have been explored by some of my colleagues and Howard. The idea is that if you can decode the entire circuits like in a correlated way, then you don't have to repeat. So you can just do things with a constant number of syndrome instruction cycle. Okay, finally, so this is I guess what we eventually want to get to, which is can we actually perform maybe universal logic computation, or at least a broad, a more general class of logic computations with a constant space and time overhead. So I guess we have some examples that we're getting pretty close to this. For instance, for this GHD state preparation, but it will be interesting to explore more tasks or even have some schemes that works for generic computation. Okay, so with that, I'll thank you for your attention, and I can take any questions right now.
Thanks. Anyone have a question? Please ask. Unmute yourself and ask directly.
Yeah, thanks, Qian, for the nice talk. Yes, I have. So when you say about single shot decoding, right? You are implying that you need to go to at least 3D because you need this meta check to check for the measurement error.
Mhm.
Is that correct?
So I'm saying this for single shot state preparation. So it turns out
Oh,
you can already get single shot error correction for 2D hypergraph particles.
yes.
But like having single shot state preparation, which means that you just prepare your codewords by doing just one round of stabilizer measurements, that is turns out to be more demanding task than error correction. And that requires properties that the so-called soundness. And then people have shown that you have to go to 3D or 4D in order to get this soundness property. We also proved this in our paper.
I see. So for the single shot, not state preparations, where you can do it even for 2D. What is the reason there you can have single shot? Because there you also have this meta check?
Yeah, that's a very good question. So the reason why you get a single shot error correction for 2D hypergraph particle is not because you have a meta check. So actually you don't have any meta checks. So this different is because of a different mechanism which is called expansion. The idea is when you have some expansion, we use some expander classical codes. You have, because of this expanding property, you can somehow show that even if you cannot reliably correct the measurement errors, the back action due to this measurement errors is still under control, which means that like small measurement errors can only lead to a small data errors in the end. So everything is still under control because of this expansion property.
I see. Yeah, another question that I have is, I still do not understand the masking. Why if you prepare the first and second ancillas in plastic and then do C naught, you mask this ancilla?
Yeah, the idea is that, so let's say you don't, okay, so, okay. So the idea is if you set this to be plus, then this, for instance, the second two primary qubits will not be entangled with the secondary qubits at all, because it just commutes with the CNOT now.
Yeah.
And therefore, if you just implement the circuits, okay, you will now measure the secondary qubits.
Okay.
And the third order qubits.
Okay.
Mm-hmm.
And what's the use of the second ancilla then? If you can just already mask it by preparing it in plastic.
Yeah, so the idea is that we don't know how to selectively prepare a block code into the arbitrary set of 0 or plus, a mixture of 0 or plus. We only know how to photon prepare all the zeros or all plus.
Oh,
in order to get the selective state preparation, we actually have to use this kind of
I see.
GPVM that we constructed.
Oh, I see. Okay, yeah, got it. Thanks.
Can you very at high level explain? So let's say if one wants to apply this to these bivariate bicycle codes from IBM, what is the issue? Is it because here you had this let's say you were explaining in terms of hypergraph product code, and there you were doing puncturing and then selective puncturing and then masking. Something can't one try something similar with, they are also not really HGP code, but they are, uh, there are also CSS codes, right? These are bivariate bicycle codes. So can't one take the corresponding classical codes and then puncture and then, I don't know, whether try to mask and see if it works.
Yeah, so the idea is that, okay, so this is a product over F2 for the hypergraph particles. But there, the products are they're not like a product over F2. So that means that although they still have product structure, but somehow this homomorphic case does not naively generalize to this setting. Because in particular, we can show that because the idea of having natural homomorphic CNOT, as I emphasized, really depends on finding a natural homomorphism between these quantum codes. And we do not know how to construct this quantum code homomorphism in general. It's pretty challenging. And the reason we can get this homomorphism in the case of hypergraph protocols is that because you have this product over F2, then we can sort of essentially get this quantum cohomorphism by taking the tensor product of this classical homomorphism. I guess in this case, that basically means that you just need to modify this classical code in some structure preserving way. But unfortunately, so this doesn't generalize to the bivariant codes, because so one thing is that there the elements is like over, I guess, over some group algebra. It's not over F2. So of course you might be able to say cause some operation that say do some function on this group algebra. Let's say on some we call some polynomial ring. But that's not useful, because in that when you do things over the polynomial ring, it's really just like one block, and you cannot just function out if you puncture out just one element, you're actually puncturing out the entire block of logical qubits. So I guess you can do that, but it will result in a trivial operation. So I guess, in other words, we do not expect you can naively generalize this function operation from F2 to this polynomial ring. Well, you can do that, but it's not a useful operation. Does that make sense?
I see. Okay, at some level. Okay, so you are saying that this homomorphic property does not hold for this like this group algebra codes, and that's why like one cannot like naively think of generalizing it there.
I think so. Yes, the idea is really how to get this natural quantum code homomorphism. So this is a mathematical problem.
Yeah.
And here we're really taking advantage that these codes are just part of the classical codes, and therefore you can get this homomorphism by taking classical homomorphism. We know efficiently how to get this classical homomorphism. So almost all the operations we can do for the classical codes are structure preserving. So this function, augmenting, shortening, and so on. They're almost all like structure preserving.
So like, do we know any concrete, okay, so like this bivariate bicycle code, like they give us really nice, I would say, encoding rate, like concrete instances of encoding rate and distance. So do we know such, like, I mean, and they have also, I think, this double toric structure. So let's say for hypergraph product code, other option could be like, let's say one tries to search better codes, like, I mean, concrete examples of hypergraph product codes, and see if already, like there are nice hypergraph product codes. So have people explored, let's say, I mean, like nicer hypergraph product codes, like, concrete instances?
Yeah, I think we gave very concrete instances of the hypergraph codes that are promising for instance, even do the quantization. By promising, I mean that you can expect better parameters than the surface code in practical regimes. For instance, you can get codes with like almost 10% encoding rate, or like maybe like a few percent encoding rate. Asymptotically, this is much better than the surface code. So we gave some examples in our paper, which I think they're actually practical. So in the sense that they can beat the surface code in practical regimes with, let's say, a few hundred qubits. Does that answer your question?
Okay. Yeah. I will have a look. Yeah.
Mhm.
Yeah.
Yes. So Qian, so for the masking, can I think about it in this way? So you entangle first the second ancilla with the first ancilla using C0, right? So that will create bell states between the two, right? Between the second and first ancilla.
Yeah, depends on the task. In this example, we're not creating bell state. We're just resetting the qubit into plus states. So we're doing the single qubit, single X measurements using this mask patch, the SIR patch.
Okay.
But in some examples, we're creating bell state. For instance, in this example, we are actually using this SIR patch to also create some entanglements in the ancilla patch.
Okay. I see. So okay. So I thought when you can you go back to the slide previously?
This one?
So here when you prepare the mask ancilla in plus state, right? And then you do C0 with the ancilla which is prepared first in 0, right?
Yeah. So these were originally prepared in 0. So this these gadgets means that we are doing basically a single qubit X measurements on the third and second third qubits. So this means that we are resetting these qubits into the plus spaces, X spaces.
Oh, okay. I see. Okay, thanks.
Okay, so let me turn off the recording now, and yeah, I think.